Hello, everyone. My name is Zhuofan Chen, and I'm an undergrad from CMU. Today, I'm going to talk about methods of lazy promotion on FIFO queues for cache eviction. So as to provide some background for you, caching is an extremely essential technique utilized in most modern computer systems to optimize data transmission. And eviction algorithms are critical for the performance of the cache. Two standard metrics used for measuring the cache performance are efficiency and throughput, where efficiency is measured by miss ratio, and throughput is simply measured by the number of requests processed per second. So two commonly known eviction algorithms are LRU and FIFO, where LRU stands for least recently used, and FIFO stands for first in, first out. Both of them are often used as fundamental building blocks for other more advanced state-of-the-art algorithms such as SRU, ARC, and etc. LRU is more oftenly used because it has lower miss ratio, which means it's more efficient, but it requires frequent promotions, which means it is slower, and it is inherently sequential because of its design. On the other hand, FIFO is both faster and scalable, but it suffers from a lower efficiency. So that naturally raises the question of how do we get the benefits of both LRU and FIFO? This led to a previous work, lazy promotion on FIFO. So the high-level concept of lazy promotion is to reduce the number of unnecessary promotions on unpopular objects while promoting and keeping the popular objects in the cache as much as possible. So from previous studies, it has been concluded that lazy promotion enhanced FIFO is able to provide higher efficiency while retaining the high throughput and scalability benefits of FIFO. One example of a lazy promotion on FIFO implementation is reinsertion right here, which is essentially the clock algorithm. This algorithm works by flagging the revisited object, and when an object is evicted from the cache, it is reinserted to the top of the queue if the object has been flagged. Otherwise, it's simply evicted from the cache. So this achieves lazy promotion by passively reducing the number of promotions required, because the flag puts sort of like an upper bound on the number of promotions, a number of times an object can be promoted before it gets checked for eviction, which in this case is limited by 1. This has been proven to outperform LRU in terms of efficiency. And yeah, this has been proven to outperform LRU in terms of efficiency in previous works. However, there are other methods that can be even better to achieve lazy promotion, since the concept is relatively novel. So for this work, I explored two other approaches to achieve lazy promotion on FIFO, which are probabilistic and batch promotion. As for probabilistic promotion, it has an extremely simple implementation where upon revisiting an object in the cache, you basically would flip a coin with the probability of heads given by the tunable parameter prop. And if it lands on heads, then the object is reinserted to the top of the queue. Otherwise, you do nothing about the object. This is really nice because the implementation is so simple and requires no extra metadata at all. And when the prop is set to be 1, it works exactly the same as LRU, but when it is set to 0, it works the same as FIFO. So this is like choosing a point from the spectrum between FIFO and LRU, trying to get a nice mixture of both. As for batch promotion, it takes a tunable parameter of batch size, which determines the number of cache hits you will have to wait before a promotion happens. So the implementation achieves this by storing hit objects within a buffer of given size equal to the batch size. And it pushes objects into the buffer. It pushes objects in the buffer to the top of the queue only when the buffer has been filled. So the efficiency of different methods are tested and compared on mostly CDN workloads from a variety of datasets, which include Wikimedia, Twitter, and etc. So these are all real production cache traces. And as you can see on the graph on the right, this is an aggregated distribution for each method with a specific parameter, where the X labels show each method, the name of each method, and the value of the corresponding parameter. The efficiency improvement ratio is calculated against FIFO as a baseline. And for each distribution, the dot indicates the median, and the bold lines indicates the quartiles. And as you can see, reinsertion is generally better than all other methods, including LRU. And for probabilistic and batch promotion, they are both capable of simulating LRU level efficiency. But when it comes to specific traces, the performance of different methods can vary significantly. The graphs on the right shows result from two distinct traces, where in the top right graph, reinsertion clearly outperforms all the other methods by a great amount, while in the bottom right graph, the results are extremely close. And most likely, in this case, using probabilistic will be ideal because it has the simplest implementation and best throughput without much of an efficiency difference. So this implies that more case-specific understanding is required for each approach. So here are some speculated future work directions. The first being compare different lazy promotion techniques under a spectrum of cache sizes, because as for now, the simulations are all performed with cache of fixed proportional size of 10% of the workload. And it will be interesting for sure to investigate the performance of different methods with other degree of magnitude of cache sizes. The second direction would be to study the sensitivity of tunable parameters, which could potentially be done by using a ML model under fixed circumstances. The third direction would be a more in-depth study of performance of each method under a specific type of workload, because as mentioned in the previous slide, there's a great difference between the compared results for distinct traces, and therefore a more solid understanding is required to determine which approach or method best suits the needs of a specific type of workload. That's the end of my presentation. Thank you.
Questions?
Petros Maniatis, Google. So you have an interesting kind of problem because you're getting higher throughput, but you have to give up a little bit of your miss ratio, right? So how do you make a decision there? How do you judge how many more misses you're willing to tolerate for increased throughput?
Thank you for your question. I guess this would depend on specific workload scenarios. Because, for example, if you have a really limited, I guess, hardware, then you would like to use something such as probabilistic promotion, because that's a very simple implementation without any sort of metadata, and it runs just faster than everything else. And in the case that maybe a promotion is extremely costly, then you would like to limit the amount of promotions as much as possible. Then you would use batch promotion, because In that case, you could reduce the amount of promotions by exponential scale, since you don't promote until the buffer is entirely full. Does that answer your question?
Somewhat. So do we have time for the connection? Okay. So let's say that you're focused on the probabilistic reinsertion scenario, right? And I have to decide what probability to use, because for different probabilities, I get perhaps more or less throughput at different effect to the miss ratio. So which one is better than the two? If one is a little bit more, has a little bit higher throughput, but also higher miss ratio versus the other way around. Can you like have an exchange rate between them? How do you decide?
Yeah, that's a really good question. I guess that would depend on like the specific system or hardware that you have. So that's like extremely, I guess, detailed analysis that you will have to make. I guess one approach would be, like, as I talked about, using ML to learn like how would you tune the parameter beforehand, given like a fixed scenario or setting.
Okay, thank you.
Okay, let's thank the speakers.